So this machine that was using 10,000 joules from the wall, but it ended up only using 6,000 for the clothes, and the rest went to the heat and other stuff. That's a 60% efficient machine, and it's impossible to have a 100% efficient machine because you're going to lose energy along the way somehow. Even if you cool that wire down so that it's a superconductor and has zero resistance, that's getting the electricity from the inverter of the machine to the motor of it, it's still gonna lose energy. That would violate laws of thermodynamics. So today, the questions that like this are going to be on your assignment. They're just as easy as this one. Just a couple at the very end. It's mostly thermal expansion today, and I'll show you some pictures of that. But first, while the camera is pointed at my experiment over here, I'm going to show you a thing. I hope they can see this up here. Let me show them. Yeah, they're not going to be able to see all of that. Okay. What am I zooming in a little more? Maybe they'll be able to see that. Oh, I didn't freeze it. Oh. How about now? Oh, that's very close. The only things that you can't see that matter, I guess that's half the things. You can't see aluminum is 0.22 and brass is 0.092. So I've got a stick here. Is this a good stick? It's still warm. I think it's fine. Oh, no, not that one. Here. This one's fine. Not really. Not really. I'll try that one. Alright, I'll use this stick. So I've got these which have where am I? Copper, aluminum, nickel, brass, and steel. What I'm going to do is I'm going to put some of this coconut oil on the ends of this thing, but not too much, Mr. Franklin. That's too much. And we're going to see which one is going to melt off first, based on specific heat here. Now, I'm going to tell you this is a little bit of a trick that I'm doing, so keep that in mind. But predict which one this coconut oil is going to melt off first.
Wait, can you restate them again, please?
Restate what?
What metals here?
Oh, yes. I got copper, aluminum, nickel, brass, and steel. And for people that can't see anything but the video, copper is, oh, you got copper. Brass is 0.092 and aluminum is 0.22. Oh, I guess you don't have copper, do you? Copper is 0.093, very similar to brass. Okay. Alright, I've got my little amounts on each one there. Here you can see I've got little bits of coconut oil on each of them. So this isn't super related to what we're doing today, but I want to show you anyway, since I'm doing the Bunsen burner for something else in just a minute here. So here we go. I should probably stand up, I guess. All right. Okay. Now, I'll put this here so y'all can see what's going on. Okay, we'll see which goes off first. So this is the aluminum, brass, copper, steel, and nickel, I think. I may mix up the steel and nickel. But if you watch the video, you'll be able to see which one drops first. Oh, there's the copper, that's the aluminum. So already we were messed up here. Aluminum was 0.9 for specific heat. But this is the way it always did it. I tried, that's the brass. I tried it and it did the same order the other times. Oh. So what we're measuring here is apparently not the specific heat of these metals. Because if it went by specific heat, oh, they did it at the same time. Look at that. Okay.
You should touch it with your hand.
Oh, I wasn't done with that. If it went by specific heat, then they would have gone in order of specific heat, at least according to our hypothesis. I must have bumped the camera. It's tilted now. What am I doing now? What we actually measured, because specific heat is how much it takes to, I'll put those back on for a minute, how much it takes to heat up a certain mass of a substance. But because of the shape of these things were long, the heat had to travel along the length of it, which isn't, specific heat doesn't measure how well the heat travels, just measure how much energy you have to add to something to heat it up. Like, it takes a long time to boil water, because water has a real high specific heat. It's about its molecules in there. You have to add a lot of energy to the molecules before they'll start breaking their bonds. That's why water sits at the same temperature for a long time before it starts boiling. You gotta keep adding heat and keep adding heat and keep adding heat. And finally it'll boil, but its molecules are real stuck together real well. You gotta add a lot of energy before they come apart. Anyway, this is what we were measuring, the thermal conductivity of this. So the difference between conductivity and specific heat. Conductivity, whether it's electrical or thermal, has to do with the electrons in the thing. Specific heat has to do with ion vibration, whatever that is. I'm not real sure about that, but that's why. That's not having, specific heat isn't about the electrons. So you can see ours went around their conductivity. So first, copper went with 1, and then aluminum with 0.52. So as the number goes down, the worse the conductivity gets. So copper was the best, then aluminum, and then bronze, I think. Oh no, brass. We got brass, which is 0.28. And then steel and nickel. So steel is 0.1 something, and nickel is also 0.1 something, but maybe we had, I don't know, these went at the same time. So the last couple times I did it, nickel took forever to go. So I don't know if nickel is one of these lower types of nickel, but I'm not sure, and it doesn't matter that much. Anyway, right, I'm going to show you one more thing here. So what we are doing today is that efficiency stuff, like a check-in, and we're doing thermal expansion. So right now, I guess I could try this one, because I didn't try this one before. As you can probably see, let me put the camera back up here. There we go. As you can see, I have a ball and a hoop here, and they don't fit through. But I have a different ball and a different hoop over here. Ooh-wee. Nasty. And whoop, they do fit through, but you can see they barely fit. It's a very close fit, a very close and blurry fit. But I can't see if it's blurry with my goggles on. I can't see if the camera's focused with my goggles on because my goggles are themselves blurry. So I'm going to heat this up just a little bit. It doesn't take much. Come on. And this thing has some water on it, so it may do some crackling. Oh, I broke it. Let's see if that's enough, though. Not quite. Oh, this water may be helping to keep it cool. I broke it again. Come on. I almost went and exploded on me. I probably should use my right hand for this. Well, I don't put it out. Just gotta be real careful. Alright, now let's try. Oh, it won't do it. Oh, it's almost doing it there. See, it cools down real quick. But it expanded and then it contracted. There we go. Now, I didn't try this in my own experiment, so if it doesn't work, sorry. But I'm going to see, since these already don't fit, I'm going to see if I can expand the hoop. I'm not sure that's how it works, though, because it may expand this way and it may expand toward the center here. But I'll try this out. Anyway, what we're doing today, there's 3 different ways that we can calculate thermal expansion: with length, with area, or with volume. Since this sphere is a very 3-dimensional object, we would be using volume if we were going to calculate how much this would do, how much volume this would expand by. If it's something long, like these things that I was using earlier, then we would use the length one. Or if it's something flat, then we use the area one. Let me see if this works. I heated this up some. Is it gonna work? Hey, it works! Alright. Alright, well, it cools down real fast, so I do not want to get this stuck, so I'm gonna stop. But, cool, we did it. Alright, let me see if I can fix up the camera. Camera, I've got you fixed up on my bucket here, look. See, you're propped up on my bucket right here. So, let's see. That's an official Virex bucket if you were worried. Let's look. Come on, screen. Well, that'll be good enough, right? Thanks, everybody. Okay. I'm glad the video's still going. Video, you better not quit on me. I'm just switching windows here. Okay. Have you guys ever seen what we got? I got some images here. Yeah, these images. You ever seen these on a bridge? You see it? Like big old hinges under a bridge. Or like this is down here is the pillar that supports the bridge, and up here is the actual bridge. It's like a big old hinge, or sometimes they have like rollers where you can roll around. This isn't exactly what that is, but this looks like it might be something it could pivot on and turn like that. Because bridges move around. You know, first of all, they bounce. You can be on a bridge and you can feel it bounce from all the cars going on. Or like, especially like in a parking garage. That's scary. The parking garage is just bouncing a lot. But one reason that those are there is for thermal expansion. Like in the winter and the summer, the things expand and contract. So like this hinge might allow it to go a little bit this way, or to go a little bit that way, if it's expanding or contracting. And I've got some images here, thermal expansion joints. So have you guys been, no, for a bridge. There. You guys been going over a bridge and you hear it go, "Kita, kita, Like if you're driving in a car, and the front and the back tires go over these things. That's what that noise is. This car is about to have that noise happen to it. It's gonna go. Where is it? Front tires, back tires. So it looks like this bridge might be kind of cold because these things. It looks like each piece of the bridge. This piece that the car is on, and this piece that the car is here. What kind of car is that? Is that a Citroen? Somebody look it up. Is this one of the French cars? Or wait, maybe that's a Bohol. That's used to be the GM, the European version of GM, but I don't know if they sold it or if it's still even a thing. Anyway, long story short, too late. This piece and this piece will expand when it gets hot, and these things look like it's cold right now because if it were hot, they would be interlocking better. So like when engineers build these bridges or design these bridges, they got to take into account, okay, so when you build this bridge, if you do it when it's cold, then you're going to have to build these things where they're pretty far apart. So this has this much room to expand. We can calculate how much room it needs because if you know how cold it is, then and you know how cold, how warm it's going to get and how much colder it's going to get, then you need to make sure that these don't come too far apart. If it gets too cold, or they don't come too close together and break the bridge, if it gets too hot, because if they come all the way in and don't have anywhere else to expand, that bridge is going to crack. Yeah. So let me do one of these questions here. How we doing, camera? Hey, you're still working, camera. Better keep working, camera. I'm going to do one of these questions here. So, on the length formula that we use, to find the change in length of those big concrete pieces of the bridge, or whatever, each material has its own property of how much it expands when it gets hot. So that is called their coefficient of thermal expansion. And I'm using alpha here. This is a lowercase Greek letter, alpha. Okay. You use the alpha, multiply by the initial length of the bridge. I like to say original length. This is not an O though. This is I think it's another Greek letter. I'm not sure. It's a naught. People say like, oh, but all for naught. You ever heard anybody? Maybe in a movie. Naught means nothing, right? But all for nothing. So it's like before anything happens, before you start counting, like this is like another word for zero. So you take the original length. I like to say original length because it looks like it's an O, but it's not. Anyway, original length. And the change in temperature also matters. Depending on if it goes up or it goes down. If it's down, this will be negative, and that'll change. That means the length will shrink. So let me do this example. So these guys are not on a bridge. They are on a train. You've probably in movies, I guess, you probably heard of train tracks when people are in a train that goes clickety-clack, 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 clickety-clack. That's just like the bridge thing. It's because the rails of those trains have little gaps between them, because if the rails of the train tracks expand too much, if it gets too hot and they expand too much, then those tracks are ruined. But so these tracks were 30 degrees Celsius summer day, so let's assume they're 30 degrees Celsius. The rail's length is expanded because it's hot. 35 degrees Celsius is the same as 95 degrees Fahrenheit. If that helps at all. So this is maybe 80 something. He doesn't hear any clicks, or maybe little quiet clicks if it's hot, because they expanded and there's no gaps. But he comes back in the winter. Negative 4 degrees Celsius might be 20 degrees or 15 degrees or something. I don't know. He does hear clicks because they contracted and now there's little gaps. So we're going to find out how big those gaps are. So we know the change in temperature. Sometimes these questions I don't think the required ones do, but the questions ask for like, what temperature did it reach, or what temperature did it start at? So the way you do that is delta T is equal to final temperature minus initial temperature. So in this case, we started at 30, and I messed that up. 30 is the initial temperature. So we ended at -4, and we could do -4 minus 30 makes -34. But you're really just saying what the change in temperature is. Well, we started at 30, and then we went down to -4. So it went all the way down to 0, so it changed by 30, and then it changed by 4 more, went 4 below 0, so it went down 34. So our change in temperature is -34. It said the rails are 5 meters long, so that's the original length of the rails. And it gives us that property for steel. So the coefficient of thermal expansion, how much steel expands when it gets hot? 1.2 times 10 to the -5. And it says degrees Celsius to the -1. Y'all remember that negative exponents means that it's just in the denominator. So if it says x to the -3, that's the same as saying 1 over x to the 3. So instead of saying degrees Celsius to the -1, I think that's confusing and fake. I'm just going to say per degree Celsius, because now it's in the denominator, and it's to the first power because it doesn't have an exponent on it, so that's fine. Anyway, let's find its change in length. Change in length. Alpha is 1.2 times 10 to the -5. L naught is 5 meters. And delta T is -34 degrees Celsius. So delta L ends up being 0.00204, if I remember right, meters. So those things would expand by that, what is that, 2.04 millimeters each time. So that's the clickety-clacky here, so there's those little gaps between the rails. Anyway, if you haven't already, please start this thermal expansion and efficiency thing.